Okay, well, it's my pleasure to introduce Marcelo Escudeiro Hernandes. He's from Universidade Estadual de Maringá, who will talk about all the Tjurina numbers for plane curves. Thank you very much, Marcelo, for accepting the invitation. You can start when you are ready.
Okay, thank you, Jorge. Thank you for the invitation to talk in the Brazilian Singularity Theories webinar. It's an important event online to congratulate the person. And in this talk, I will present some results about the Tjurina number of plane curves and obtained in two different work. One of them with Abramo Refes, and the second one with Patricio Almiron. We consider the invariants with respect to distinct equivalence relation about the plane curves. And in this talk, a curve is a germ of plane curve given by a reduced power series in two variables on the complex number. And the topological equivalence between two plane curves is defined in the following way. CF is topological equivalent to CG if on non-leaf. There exists a germ of homeomorphism that maps the curve CF and the curve CG. When the psi, the phi, the homomorphism is also an analytic isomorphism, then we say the curve CF is analytically equivalent to CG. I think two of the most important invariant with respect to the topological and the analytical invariant is the Milnor number. The Milnor number is the codimension of the Jacobian ideal, and the Tjurina number is the codimension of the extended Jacobian ideal. The Jacobian ideal, and we include the equation of the curve. And with respect to the Tjurina's number and the Milnor number, we have the sum upper bound, the natural upper bound. The Tjurina's number is the Milnor number. And we have the equality holds if only if the curve is analytically equivalent to another curve defined by a quasi-homogeneous polynomial. In the plane curve situation, this is proved by Zariski and Saito. But there is another bound, the lower bound, the interesting lower bound, proved by Patricio Almiron. And the lower bound for the Tjurina number using the Milnor number is precisely the 3/4 times the Milnor number. When the curve is irreducible, we can improve this lower bound. But here in this talk, we are interested in another aspect to the Tjurina's number. Consider a power series, a reducible power series given by a product of R irreducible Fi, and is very well known, the Milnor formula for the Milnor number, and that relate the Milnor number of the curve CF and the Milnor number of each branch given by this equality. The sum of the Milnor number of each irreducible component plus 2 times the sum of the intersection multiplicity between the branches minus the number of the branches plus 1. And here we are interested in the following question. How to obtain a similar expression of the Tjurina's number in terms of the Tjurina's number of each irreducible component. In the following way, the Tjurina's number admits an analytical invariant or a topological invariant that can be expressed in terms of the sum of the Tjurina's number of each branch, but plus this invariant. This is the question we considering in this talk. For this proposal, we have to introduce some object associated to a plane curve, and one of them is the local ring of F, and the local ring is precisely the quotient ring, the power series xy by the ideal generated by the equation of F, and is well known. The analytic equivalent can be rewritten in terms of the local ring. More precisely, two analytic curves are equivalent if only if their local ring are isomorphic as a C algebra. And using the notation of the local ring, we can rewrite the quotient ring by the extended Jacobian idea in terms of the local ring, and the Jacobian idea generate as a OF ideal. So the Tjurina's number can be computed by the length as an O model of the quotient of OF by the ideal, the Jacobian ideal generate as a OF model or OF ideal. So another important object associated to a plane curve singularity or a local ring of a plane curve is the value set of the local ring and the fraction ideal. And so as a local ring of a curve is a one-dimensional ring, the total ring of fractions of O, we denote by K, is the product of Ki, and each Ki is precisely the field of Laurent series, and each Ki corresponds to the field dot fraction of the local ring of each branch. And in this talk, a fraction ideal I is a O model of the total ring of fraction, such that there exists a non-zero divisor G in I, such that G times I is contained in O. That means that the I admits a common divisor, G. In some sense, this is the same. And considering the I projection of K to Ki, so we put the, using the index I by denoting the projection of the fraction ideal. And the projection of a fraction ideal of O is also a fraction ideal of OI. OI in this case is the projection of the local ring O, the reduced curve, but in this case, OI coincides with the local ring of each branch, Fi. And considering the discrete valuation nu I from the field Ki to the extended integer numbers defined by the zero maps to the infinite in the value of a fraction of an element in Ki is precisely the difference between the multiplicity in Ti of P minus the multiplicity or the ordering in Ti of H. So we, considering this notation, we put AI as the value set of the fraction ideal I, or the valuation of the projection of this fraction ideal. And we, using the value set, we able to present the first result, and the first result consider a kernel of the projection, Pi, the total ring of fraction in the fraction, the field of fraction of Ki, we consider the kernel of the projection and intersect to the fraction ideal. We denote by Ti. And we put this notation using the interval to denote the natural numbers from 1 to the I minus 1. So T, the interval, denotes the intersection of all Tj, j from 1 to the I minus 1. And by a convention, we denote by the T using the empty interval as the whole fraction ideal. So using this notation and this concept, this object, we have that if we consider two fraction ideal of O, such that J is contained in I, denote by Di the value set of the fraction idea J, and EI the value set of the fraction idea I. So we can express the colength of the I respect to J as a sum, and R denotes the number of branches of the curve with local ring O. And the sum of the colength of each projection, EI and JI, plus the cardinality of the difference, the value set of J and the value set of this fraction ideal, minus the cardinality of the value set of I minus the valuation of the T associated to the fraction ideal I. Let's present an example, a well-known example. Consider the local ring and the integral closure of the local ring O. O and O tilde are a fraction ideal of K. So let's to compute the colength of O tilde over O. Using the previous formula, we have this colength is precisely the sum of this expression. And the blue part, we can compute it. The blue part corresponds to the valuation of OI is precisely the same group associated to the branch Fi. We denote it by gamma I. So the T interval O is precisely, by definition, the elements in the local ring such that the projection of H is 0 for every branch for 1 to the I minus 1. So the projection is 0 correspond to the power series H vanish on the branch Fj. So this fraction ideal is precisely the ideal, the principal ideal in O generated by the branches F1, F2, and to Fi minus 1. So the value set of this fraction idea is precisely the value set of O, or the projection in I of the OI, so is precisely the same group, plus the evaluation of this product that correspond to the sum of the intersection multiplicity of Fi to the O branches Fj. So the difference, the cardinality of this difference is precisely the sum of the intersection multiplicity of Fi and Fj. So we can replace this blue part by this sum. And the red part can be computed in the following way. We know that the integral closure of O is precisely the product of the power series in Ti, and the power series in Ti is precisely the integral closure of the local ring of Fi. So when we consider the projection of the O tilde, we obtain the power series in Ti, and the valuation, the set of values, is precisely the natural numbers. On the other hand, when we consider the T interval corresponding to the O tilde, this is the set of all elements in the integral closure, or every R upper of the power series, such that the projection is 0 for all indexes from 1 to the I minus 1. So the T interval 1I correspond to the R upper, when here we consider 0, and HI to HR belong to this power series in T. So when we consider the values with respect to this element, this is precisely the values of the projection in the I coordinate. And the projection of and the I coordinate correspond to the values of the CTI. In this way, we have the same, the natural numbers. In other words, the red part, the cardinality of this difference is precisely 0. So we obtain the well-known formula by Hironaka, because this codimension is precisely the delta invariant, and by the previous computation, we have the sum of the length of the projection of the integral closure in the component I, and the projection of the local ring also in the component I. So this codimension is precisely the delta invariant associated to the component I. So we have the sum of the delta invariant of each branch. And here we have the sum of the whole multiplicity, the intersection multiplicity of Fi and Fj, when J and I vary from 1 to the R. So this is only an example to illustrate in the well-known case the previous formula. But of course, we are interested in another fraction idea. We are interested to apply the previous formula to the Jacobian idea, to the extended Jacobian idea, in order to compute the Tjurina number. So denote by GF the extended or the Jacobian idea respect to the local ring OF, and we put JFI to denote the projection of the Jacobian idea and the I component. This is not the same to the Jacobian idea respect to the Fi, but the projection is the Jacobian idea of the branch Fi times the product of all equation of the another branches. And we put the values, the value set of the projection with respect to I, we indicate by delta I. So as before, T and an interval 1I denote the all element in the Jacobian idea, such that the projection respect to J component is 0. This means the element in T interval correspond to elements in the Jacobian idea of the reducible curve, such this projection or this element vanish on the branch Fj. This is precisely the interpretation for T interval. So using the previous theorem and this notation, we can express the codimension of the Jacobian, the extended Jacobian idea, as also a sum of the codimension of OI and J Fi, the projection of the Jacobian idea, plus a cardinality of this set minus the cardinality of the value set of the local ring of each branch and the T interval associated to the local ring. Note that this corresponds to precisely the Tjurina's number, and this red expression is not precisely the Tjurina's number of each branch. In fact, this codimension is the codimension of OI by the ideal, by the model, by the fraction ideal given by this one. So this codimension is the codimension of OI by the Jacobian ideal respect to the component I. This is the Tjurina number of Fi, plus the codimension of OI with respect to the ideal generated by this element. And this is the sum of the intersection multiplicity. So we can replace this blue expression by the Tjurina's number of each branches plus the sum of the intersection multiplicity. The last expression we already computation in when we consider the delta invariant, and we saw this cardinality is precisely the sum of the intersection multiplicity of Fi and Fj. So we can expand this sum, and we obtain 2 times the last one. So we obtain this expression for the Tjurina's number in terms of the Tjurina's number of each branch, the sum of the intersection multiplicity plus this number. And this number, this cardinality, this is precisely an analytical invariant associated to obtain a similar form to the Milnor number, but now for the Tjurina's number. In fact, when we expand the sum, we obtain this expression. And notice that when I is equal to 1 here, we denote this model, this fraction ideal, is precisely the I. So the valuation is precisely the delta I. That means this expression for the index I equal to 1 is 0. In fact, we can put here 2. Okay? So the red part is precisely the invariant we are looking for the complete description of the Tjurina's number in terms of the sum of the Tjurina's number of each branch plus some invariants, a topological invariant and analytical invariant. So when you compare with the Milnor formula, we have some similarities. For instance, here we have the sum of the Tjurina's number and the Milnor number. Here we can expand this part, and we'll obtain the sum of the intersection multiplicity here. And here we have extra terms, a sum of the multiplicity minus the number of branch plus 1, and the sum of this new analytic invariant. So we can manipulate, recall that when we have I equal to 1, we obtain this cardinality is equal to 0. So we can rewrite the derived part in this way. So it's natural ask for the following relation between the intersection multiplicity minus 1 that appear in the Milnor formula and the cardinality of this difference. Of course, we know the Milnor number is greater than the Tjurina's number, and the Milnor number of each branch is greater than the Tjurina number of each branch. But is is a mystery or a question about each extra term here comparing to the cardinality, because maybe we can obtain, for instance, this part is greater than this one, and this one is less than, and we have some kind of compensation in order to obtain the Tjurina's number less than the Milnor number. So a question is, how can compare the intersection multiplicity that appear here and this cardinality? And this kind of inequality, this question, is related to a Dinka conjecture. More precisely, Dinka asked about the difference between the Tjurina's number of the reducible curve minus the sum of the Tjurina number of each branch, and the difference between the Milnor number of the branch and the sum of the Milnor number of each branch. And the Dinka conjecture is precisely that this difference is less or equal to this difference. So notice that if you have this inequality, this cardinality is less than or equal to this intersection multiplicity minus 1, so we have the Dinka conjecture. And we can prove precisely this inequality. So we have this proposition. The cardinality of delta I is precisely the elements in the Jacobian idea when we project in the I component, minus the value set of the elements in the Jacobian idea that vanish in the component F1, F2, until to Fi minus 1 is less or equal to this intersection multiplicity. So, as we said before, this proposition plus this theorem give us answer to the Dinka's question. So we have this inequality, the Tjurina's number minus the sum of the Tjurina's number of each branch is less or equal to this difference. Of course, when the curve CF is quasi-homogeneous, we have the equality, but I don't know if it's the only case we have this equality here. I don't know. Okay. So another interpretation or approach to express the Tjurina's number of a plane curve is using the differential forms. So let's consider the differential one forms such that the edge product with the differential of Fi belong to the ideal generated by Fi. It's the same to say the element in the Jacobian idea belong to the Fi. This is called the cytomodal associated to the branch Fi. We can rewrite this cytomodal, this set, in this way. Consider the differential one forms with the following property. There exists no multiple of Fi such that the G times the one form belongs to this model. When the coefficient of the form, the omega, are coprime, this means that foliation defined by the omega admits CF as a separatrix. Is the same. But here we consider O one form. Using this concept of the cytomodal, we have the following result. The value set of the T interval 1 I is precisely the value set of the O edge product of an element in the cytomodule with the differential of f of f. F is the equation of the reducible curve. And here, as before, this notation indicates the intersection of O cytomodule. And using this interpretation of the T interval 1I, we can obtain that the cardinality of the difference of delta I minus the value set of T interval is precisely the cardinality of lambda I minus the valuation of the cytomodule. And lambda I denotes here the valuation of one forms. We can extend the notion of valuation of the discrete valuation nu for the one forms, and we can compute the value set, and here lambda I denotes this one. So in this way we can rewrite the formula for the Tjurina's number using the differential forms in this way. The Tjurina number of the reducible curve is the sum of the Tjurina number of each branch, but plus the sum of the intersection multiplicity between two distinct branches, plus the sum of the cardinality of this one. And we can compute in two distant way this cardinality, this new invariance. Is only an interpretation using different forms in order to compute the Tjurina number. Is a nice interpretation because we can apply in particular situation and compute the Tjurina number for reducible curve when each branch has some particular or special properties. For instance, let's consider the case when we have two reducible branches, F1 and F2. Each branch are quasi-homogeneous, but the product F is not quasi-homogeneous curve. Okay, so we can compute in this way the Tjurina number of F using the previous formula. As each branch is a quasi-homogeneous, when we apply the previous formula, we obtain the Tjurina number of the curve is the sum of the Tjurina number of each branch. But each branch is quasi-homogeneous, so the Milnor number of each branch coincide with the Milnor number. So here is the Milnor number of F1. Here is the Milnor number of F2, plus the intersection multiplicity of F1 and F2 is precisely alpha 1 and alpha 2, plus the analytic invariant given by the cardinality of the difference of value set. In this case, it's possible to describe the cycle number respect F1 and compute the values respect to the branch F2. And we obtain these values, and this will get a formula for the Tjurina's number. In this case, when we have two irreducible plane curves, quasi-homogeneous, with distant tangent, but the F, the product, are not quasi-homogeneous curve. On the other hand, when we consider two quasi-homogeneous curves with the same tangent, but F is the product is not quasi-homogeneous, so we can also express the Tjurina number of the CF using the previous formula. So appear the number, the Milnor number that coincide with the Tjurina number of F1 and F2. Here is precisely the intersection multiplicity of F1 and F2, and here is the cardinality of the the difference between the all values of the differential in the branch F1, for instance, minus the values of the cytomodule. And using the differential forms, we can also obtain the formulas for the Tjurina number in several other situations. For instance, with almiron, we prove the following result. If you consider a curve with two branches, two singular branches, C1 and C2, so this means C1 and C2 has the same semigroup of values, for instance, and we denote the semigroup by V0 to Vg. In particular, if the semigroup are the same, the Milnor number of C1 coincide with the Milnor number of C2. And suppose that the intersection multiplicity of C1 and C2 is greater than the GCD of V0 to dV G minus 1 times Vg. Okay, so when you fix this singular class to C, given by the semigroup of C1, the semigroup of C2, given by this one, and consider the intersection multiplicity big enough, okay, we obtain the Tjurina number of C is constant in this topological class. And his value is precisely 2 times the intersection multiplicity of C1 and C2 plus the Milnor number of C1 or C2, or because are the same, minus 1. And if we replace these values using the Milnor number formula, we obtain that the Tjurina number for this situation, this singular class, this topological class, is precisely the Milnor number of C minus the Milnor number of C1 or C2. So the difference of Milnor number and the Tjurina number is constant and equal to the Milnor number of some of the branches. So another situation, when you consider the model of the differential and compute all the values and compute all the values of the elements in the local ring, we obtain the semigroup of values of the curve. So the semigroup corresponds to the R upper of the evaluation using the same element in O, and lambda bar corresponds to the R upper when you compute the evaluation, the extended evaluation of the same differential form respect to the F1 to the FR, and you consider the zero in this set. So it's possible to express the difference between the Milnor number and the Tjurina number using this value set. We put the distance between lambda bar and the gamma, the semigroup. And this distance corresponds to difference between the length of the saturated chain in lambda bar and the gamma. So it's possible to obtain in a combinatorial way the difference between the Milnor number and the Tjurina's number. This generalizes a formula given by Berger for irreducible plane curve. Berger presents a similar formula for the difference between the Milnor and the Tjurina number, using the difference, the cardinality of the difference of the value set of differential and the value set of the function. Also, that means the cardinality of the lambda minus gamma for the reducible. Here we can consider this expression as a generalization of the the Berger formula for the n-plane curve with R branches using the evaluation set and so on. So I think I stop here. Thank you for your attention.